think it's the Intel group with Raul Diaz. A real-time media transport stack based on commercial off-the-shelf hardware. Thank you, Raul.
Thanks, everybody. We've been talking a lot during this conference about what happens when a video stream is ready to be compressed, and then all of the things that happen after that. I'm going to talk about what happens before that stream is even available. I'm going to talk about media production. In media production, you have a number of cameras, microphones, graphics servers providing information that needs to be produced into a single stream. And historically, this production has been done using custom video processing equipment and SDI networks that are synchronous networks timed to the video pixel rate. So it's very easy to keep everything synchronized. All of the audio and video data is all interleaved. It really has a decades-long history, very successful history. However, as the resolutions have, video resolutions have increased, and just the scale of video production has grown, it's been difficult for it to keep up. And so there's been a need to really transition into an environment where we can virtualize the video production by using video over IP, well, audio, video, ancillary data over IP, and using general purpose compute servers to perform the video processing. So it's really a case where all of this compute power and networking capability has come together to allow this to happen. And so a new standard called SMPTE ST2110 has evolved, and it really takes advantage of the ubiquitous nature of Ethernet and IP-based datagrams. And you can support any bit rate, any specific media protocol, in fact. It's very easy to scale. It is quite inexpensive. Now, SMPTE ST2110 was standardized in 2017, and it is a very complex standard. It's designed to interface with video equipment that has very precise video timing. And so how do you reconcile sending packets over an asynchronous network while still being able to interface with synchronous equipment? So, and then to make things even worse, video production is normally done using uncompressed video. There's increased use of compressed video, I'll grant you that, but you're not going to see the Olympics or the World Cup or any of the major events done, or even everyday events done with compressed video. The quality hit is just not acceptable to the top tier broadcast studios. So uncompressed video has to be transmitted, and uncompressed video is I'll just mention two different sizes. One is full HD 1920 by 1080, progressive 60 frames per second, is about 1.2 gigabits per second uncompressed, and 4K is on the order of 12 gigabits. So if you're moving many cameras with that kind of video, it's quite challenging. And the part that makes it really hard is a part of this very complex standard called ST2110-21, which enforces all of this timing. And that's what I'm going to talk about today. So most of us are pretty familiar with video and how video is formatted. But just a quick refresher here. Normally, you have a video frame, and within that video frame time, you're going to transmit all of the pixels in that video. But in addition to that, you have certain time in the front of the video, and typically on the back of the video frame as well, that because of historical standards and things like vertical blanking intervals and things like that, have evolved to give space for things like ancillary data transmission and other things. So this timing has to be respected. And so there are really two parameters that are critical when transmitting video in the ST2110 standard. The first one is something called TR offset. This is the time before you can transmit the first packet of pixels after the video frame has actually started. The frame time has started. And then after that, there's a TRS parameter, which is the inter-packet gap. And it has to be very precise so that you don't overflow any of the video equipment buffers. So we want to do this with standard NICs. Now these are server grade NICs, so they have some functionality. They have some traffic shaping capabilities, some rate limiting functions, but these are statistical in nature, and they're not precise enough to meet the needs of video production timing. So what we want to do is to be able to take advantage of the very limited feature available in standard server grade NICs, but then add additional algorithms and software to be able to make them meet and comply with ST2110-21. So in our solution, what we've done is we've introduced two new algorithms, and this is one part of a very large piece of software that does many, many things, but this is implementing just the ST2110-21 part. And these two algorithms are for the interpacket gap, the TRS parameter. We have a credit-based profiling and dynamic padding algorithm that improves the precision time dramatically. It changes it from being stochastic to being quite precise. And we can gain a lot of granularity with this two-part algorithm, the credit-based profiling and the dynamic padding. And I'll talk about that one in a moment. And then the other algorithm is the one for how you make sure that that first packet goes out at precisely the right time. Again, you have launch times in NICs, in server-grade NICs, but they're, again, you can sort of get close, but they're not really that precise unless you have a true time-sensitive networking NIC, and those are quite rare, and certainly not in data centers or large edge clusters. So we've designed a dynamic tuning algorithm that sets up a particular warm-up packet queue. These are dummy packets that are there just to take time and hold the space for precisely when the first packet will go out, and I'll talk about that algorithm in a moment. Okay, so we'll start with the first algorithm. So this has these two components. There's the credit-based portion, and in the credit-based portion, what we do is we first profile the rate limiter. So we run some tests on it, and we profile it, and once we've done the profiling, we set the specific rate limit that we think is going to give us the best average performance. And then we create a specific timing loop that allows us to form a credit-based algorithm where after a certain elapsed time, we get a credit, and then we're allowed to send another packet. Now, that works quite well, but by itself, still not accurate enough. We still were not conforming to the standard. And so what we did is we added a special set of, again, these dummy packets that just hold time. And we pad the specific video and the specific video packets with some of these dummy packets. We call them pause packets, but they're not really standard pause packets. They don't actually traverse the network. They're simply taking time inside the NIC queues. And then once we do that, we have very, very precise timing. So that's interpacket gap. And by the way, this interpacket gap is very, very tight. For HD, you're talking about 3.5 microseconds between each packet. And for 4K, it's on the order of about 500 nanoseconds. So it's not something that you can just use interrupts on your CPU and just send a packet that way that won't work. You don't have that kind of granularity, and you'll also have hardware interrupts to your CPU that will take you completely out of spec, which is why this algorithm is needed to push the packets correctly into the NIC queues. Okay, so now we talk about how do we get that first packet to go out before the interpacket gap pacing begins. And to do that, we also do a profiling of the queues, and we start to put packets in there, and we can set the NIC to tell us precisely at what time the packet was actually sent on the wire. There's a logging function in most NICs. And so we start sending packets. We count how many got sent and how many we had to put in the buffer to get the one that goes out at precisely the right time. Once we have that profiled, then we simply create our warm-up queue for every single frame, and then that first packet of real video data goes out at precisely the right time. And this allows us not to rely solely on the launch time windows of server-grade NICs, which are not particularly accurate. Okay. So from an experimental results, this is the results of what would happen if we didn't do this dynamic padding for the interpacket gap. What happens is that you start to accumulate the amount of time between the packets, and it continues to grow forever, and you'll be out of spec very, very quickly. And so this is another parameter, and I'm not really going to explain all of it because it's a bit technical, but there's a specific algorithm that has to be implemented, a standard leaky bucket algorithm, and there's a fill line that you can't go over. And if we don't do the packet padding, what we'll do is, because of the statistical nature of the packets, will overflow at any moment in time, and it happens very frequently. So once we add the packets, we keep it extremely tight. We never, ever go out of spec. And we've run it literally for weeks on end, sending continuous video. And likewise, for the first packet out, if you don't warm up the queue, again, you can set launch times, but the launch time window granularity on most NICs is not sufficiently tight. And so you'll be right most of the time, maybe some of the time, but sooner or later you're going to get pretty large deviations off of your precise launch time for that particular offset that you need. And so by using our warm-up queue, we're able to stay within an extremely tight window with just a few nanoseconds in each direction. So the jitter is very low, and likewise the jitter is low on both of these parameters. Okay, so in conclusion, we've created this real-time media transport system, and we have tested it with many, many resolutions, frame rates, video formats, all the way up to 8K, and we consistently pass all of the ST2110 compliance tests, both with the EBU software tools and hardware network analyzers. And we've also done pretty extensive testing, interoperability testing with third-party equipment. And this has also been done by our customers. So we've done our own independent testing, our customers have done it, and we pass all the tests. And so that means that the RMTS is a fully compliant ST2110 implementation, and the code is completely open source and available to anyone who would like to use it at that location. Thank you.
Thank you very much.